CVPR 2025 paper discussion from the Robotics and Vision workshop. The paper's called Centaur, Robust End-to-End Autonomous Driving with Test Time Training. It's out of the University of Hong Kong and the Chinese Autonomous Driving Lab. I think it's based in Shanghai. This paper is really interesting because what they're trying to solve is an end-to-end trained planner for self-driving works really well until it doesn't, right? And when it doesn't, that's usually when the vision, let's say we're a camera-only system, and the cameras detect a situation that the planner cannot make sense of. The way the authors define that is by a high uncertainty. And what that means technically is that the planner has certain trajectories that it projects for the next move. And what you want is, if you cluster those trajectories, you want to make sure that there's a very high probability for one trajectory and a very low probability for everything else. And that's low uncertainty or low perplexity, and therefore very high certainty, and you can move on. What if you have, let's say, 10 trajectories and the likelihood of each one is almost the same? That's the equivalent in human terms of, well, I can do all these things and I'm not sure what I should do. You have high uncertainty. So in that case, what the authors are saying is, well, we have an end-to-end trained model, so we don't really know exactly which parts of the weights in the trained model are going to help us make a better decision. But what we can do, we can use this uncertainty as a trigger to use real-time incoming data and optimize maybe another function, and we'll talk about what that is, in order to make a decision right on the spot. In other words, we use our pre-trained model and the weights, which are fixed, whenever we can, but when we can't, we have to go into test time training. We have to actually think on the fly. This is akin to reasoning models in the large language model world. It's not the same exact thing, and technically it's different, but it's the same philosophy. And the philosophy is that you look at the world and you spend a little bit more time trying to make sense of the world, because your understanding of the world right now is not enough. Now, the way they do this is, and I'm quoting, since ground truth labels are unavailable during test time, cluster entropy serves as a self-supervised loss function, guiding adaptation without requiring external supervision. So what that means is that, and the authors say in the paper that prior to this paper, end-to-end training models, and this might as well be FSD, Tesla, maybe it's like that, we don't know, but they could have a hard-coded function which says, look, if you have high uncertainty, just do this. And in the case of Tesla, very often I think they just stop. They just do nothing. They just say, you know what, take over. I don't know what's going to happen, right? This is your full self-drive, supervised full self-drive stack, right? It's the human in the loop stack. It's, if uncertainty is at a certain level, just take over. What if you can't? What if you can't take over? Do we want to have an adaptive, a native system that can adapt to the current situation in the traffic and solve the question, what should I do next? Well, we could by having a cost function which specifically reduces the entropy. So we have, let's say, a flexible function on top of the weights, which when triggered takes input data and reduces entropy. So let's think of a concrete example, and I'm thinking on the fly here. I haven't seen concrete examples in the paper about this. So the car's driving, and let's say we have sun glare, right? So the car takes information in and has several options of what to do next, because it doesn't see really well what's in front of it. It could go straight, left, or right. So now we're using additional information in real time to reduce the uncertainty. Now the uncertainty is we're not seeing very well. So how can we reduce this uncertainty? Well, we could use we could maybe import more pixels, or we could whatever input we have, we use it to reduce the uncertainty. This could, for example, happen by exclusion, right? We have maybe we see the opposite traffic, and we can extrapolate from the opposite traffic what's more likely going to happen to our road. Like if the opposite traffic is going parallel to us, that means we should be going straight. If the opposite traffic is turning to the left, then we should be turning right. If you have traffic's turning to the right, we should be turning left. So things like that could be used to reduce the uncertainty with real-time incoming data. Again, the links in the show notes, the paper will explain in more details the technicalities of this. I think what's interesting here is, first, what is end-to-end training? Let's do one step back and just think about this. What does end-to-end training actually mean? End-to-end training means that we take in information and we use gradient descent across the model, end-to-end, optimize across the model, and have an output, a prediction of a planner. We're not using modular systems. We don't have a special vision encoder and a planning encoder, or a behavioral model or anything like that. We literally take pixels in, actuators out. In order to improve uncertainty, we can have hard-coded functions that kick in when uncertainty is high. So uncertainty is the trigger. No matter what, uncertainty is the trigger. But we could have a different way to deal with that. And in particular, what this paper is trying to achieve is we want to have a test time training solution to the uncertainty. So we don't want to have hard-coded things or fixed functions. We want the functions themselves to be learned and to adapt to the incoming data. So to summarize, Robotics and Vision Workshop, this is the first paper from this workshop. We're going to discuss a few more. This one, again, robust end-to-end autonomous driving with test time training, and the idea being that you have you use uncertainty as a trigger, and then you have incoming data which reduces this uncertainty. So the additional function that is being optimized is being triggered, and it's being optimized in a way that you reduce the uncertainty and therefore can make a decision. Thank you.